Right here. This is where raw steel transforms into something extraordinary. Welcome to Jingyan Yinduan's automated forging line, where bushing components are born under thousands of tons of pressure. Heated billets drop into the die, and in a fraction of a second, bang, the forging hammer strikes with precision that no human hand could match. Each bushing emerges perfectly shaped, with grain structure aligned for maximum strength. This isn't just manufacturing, it's industrial artistry, perfected over decades. If you've ever watched a master craftsman on a lathe, that focused, deliberate turning of metal into something precise and purposeful, then you already understand the soul of what the Haas Street 10Y is doing here, just at a whole different level. This machine is part of Haas Automation's legendary Street Series turning centers, and it brings serious industrial muscle to the shop floor. Standard equipment right out of the box includes a 6-inch hydraulic chuck that's 165 millimeters, paired with a 12-station bolt-on turret. That turret is the brain of tool changes, cycling through cutting tools with speed and repeatability that would have seemed like science fiction to machinists back in the 1970s. Now, powering all of this is a vector drive spindle rated at 15 horsepower peak, capable of spinning up to 6,000 RPM. For those of you who remember running manual lathes, that kind of surface speed opens up a world of high-feed cutting possibilities that simply weren't available a generation ago. The A2-5 spindle nose accepts bar stock up to 1.8 inches in diameter, about 45.7 millimeters, giving you plenty of range for a wide variety of turned parts. But what really sets the ST10Y apart is that Y-axis capability. While traditional lathes work in 2 dimensions, the Y-axis adds off-center milling and drilling, meaning complex parts that once required 2 or 3 separate setups can now be completed in a single chucking. That's not just convenient, that's a fundamental shift in how production efficiency is measured. And if you want to push productivity even further, the options list reads like a machinist's dream. Bar feeder systems to keep the machine running lights out through the night. A hydraulic tailstock for supporting longer workpieces. Automatic tool probing to verify tool length and catch wear before it causes scrap. C-axis live tooling for true mill turn capability. An automatic parts catcher to collect finished components safely. And a high-pressure coolant system that blasts chips away and keeps cutting temperatures in check. Here's something that ought to make us all feel a bit better about the future: watching Norsk Hydro recycle aluminum. And folks, this isn't just feel-good environmentalism, it's brilliant engineering and economics rolled into one. Think about this: producing virgin aluminum from bauxite ore is incredibly energy-intensive. You're essentially using electricity to break apart the chemical bonds in aluminum oxide. It takes massive amounts of power. But recycling? That saves 95% of that energy. 95%! That's not a typo. Watch as that scrap aluminum gets loaded into the furnace. Could be old window frames, scrapped car parts, used beverage cans. Doesn't matter. Aluminum is aluminum, and it can be recycled infinitely without losing its properties. That's different from plastic, which degrades each time you recycle it. The furnace heats up to around 300 degrees Fahrenheit. Hot enough to melt aluminum but controlled carefully to avoid oxidation. See that molten metal glowing? That's the same quality as newly smelted aluminum, but it got here using a fraction of the energy. Now here's where it gets technical. As the aluminum melts, impurities rise to the surface as dross. That's the crusty stuff you see being skimmed off. Salt flux is often added to help separate out contaminants. The operators are constantly monitoring the chemistry, sometimes adding small amounts of alloying elements to hit the exact specification needed. Once the melt is clean and the chemistry is right, it gets poured into molds or casting machines. Some facilities use continuous casting, where molten aluminum flows into a water-cooled mold and emerges as a solid billet or sheet, moving continuously like an aluminum river turning to metal. Norsk Hydro, being one of the world's largest aluminum companies, has refined this process to an art. They've got facilities that can process hundreds of thousands of tons of scrap annually. Every ton of recycled aluminum prevents about 4 tons of bauxite from being mined and keeps about 8 tons of carbon dioxide out of the atmosphere. Remember when recycling bins first showed up in our neighborhoods back in the 80s and 90s? This is where those aluminum cans end up, and incredibly, a recycled can could be back on the shelf as a new can in as little as 60 days. There's something almost hypnotic about watching a CNC oxy-fuel torch glide through thick carbon steel, a ribbon of orange sparks trailing behind like a comet's tail. Here, we're cutting 6mm carbon steel plate, that's roughly a 1/4 inch thick, using a computer-guided oxy-fuel cutting system. The process works by preheating the steel to its ignition temperature with a high-temperature oxygen-acetylene flame, then introducing a high-pressure stream of pure oxygen. At that point, the iron literally combusts, and the cut front moves through the material with remarkable speed and control. What makes this CNC-guided version so impressive is the consistency. The machine follows its programmed path to within fractions of a millimeter, producing clean, square edges across every part, whether it's cutting 1 piece or 500. Imagine standing at the edge of the North Sea, watching something the size of a skyscraper being lifted out of the water and locked into place. Not in a city, but 12 miles off the coast of Scotland, where the wind never stops and the ocean doesn't forgive mistakes. That's exactly what happened at the Moray East offshore wind farm, and it is one of the most ambitious engineering achievements of our generation. At full capacity, Moray East generates 950 megawatts of electricity, enough to power roughly 950,000 British homes. The project sits in the outer Moray Firth, a stretch of the North Sea known for strong, consistent winds that make it one of the best offshore wind resources in the entire world. When it came time to choose the turbines, the project partners selected the Vestas V164-9.5 megawatts at the time of installation, among the most powerful offshore wind turbines ever commercially deployed. Let's talk about the hardware for a moment, because these numbers are genuinely staggering. The V164 refers to the rotor diameter, 164 meters or about 538 feet tip to tip. The rotor sweeps an area of more than 21,000 square meters. That's nearly 5 acres of wind-catching surface, spinning continuously in the sea breeze. At rated wind speeds, a single turbine generates 9.5 megawatts, and with 100 turbines across the Moray East project, the total installed capacity reaches that remarkable 950 megawatts figure. Now, assembling these machines offshore is where the real story lives, because this isn't like bolting something together in a factory. Every major component travels by sea. The monopile foundations, each weighing over 1,000 tons, are driven into the seabed by hydraulic impact hammers aboard specialized installation vessels. Then comes the transition piece, which connects the monopile to the tower sections, followed by the 3 tower segments that stack one on top of another, rising to hub heights of around 105 meters above the water's surface. The nacelle, that's the housing unit at the top of the tower containing the gearbox, generator, and all the critical mechanical systems, weighs in at approximately 390 tons on the V164. Lifting that into position over open ocean, accounting for wave motion, wind loading, and the sheer geometry of the operation, requires one of the most specialized vessels on Earth, a jack-up installation ship. These vessels lower massive legs to the seabed, physically lifting themselves out of the water to create a stable working platform, then use their enormous crane systems, some rated at over 500 tons of lift capacity, to hoist components into alignment. Finally, the 3 blades are attached, either one at a time using a single-blade installation approach, or pre-assembled into a star configuration on deck and lifted as a complete rotor assembly. Either method demands millimeter-level precision while the vessel holds position in North Sea conditions. This is modern manufacturing and modern construction merged into one extraordinary project, redefining what's possible when human ingenuity meets the raw power of nature. The the turbines spin. The cables carry the current, and somewhere on the Scottish coast, the lights stay on, powered by the wind.